Today we're going to talk about Newton and his three laws of motion. Now, Newton wasn't born into a very wealthy family. He was born in kind of a farmer and had some difficulty socially growing up. But as he got older, he did some really important things in science. His book, Principia, is considered to be one of the most important historical science books ever written. And he invented calculus before his three laws of motion, which we're going to talk about. He also invented the reflecting telescope and other really important historical works. But we're going to focus today on his three laws of motion. His first law of motion says objects at rest will remain at rest, and objects in motion will remain in straight line motion unless acted on by a net force. His second law is mathematical and says that the sum of all forces equals mass times acceleration. The third law can be written mathematical. It says a negative force equals positive force, or in words, we could say for every force, there's an equal magnitude and opposite direction force. Let's take a look at these. Okay, one of the most dramatic demonstrations of Newton's first law of motion in objects at rest want to stay at rest has been a wine glass filled up with some Pepsi and having a tablecloth underneath it pulled out and it staying at rest. Bear in mind, the first part of his law, inertia, objects at rest, once you remain at rest, deal with something like this, where you have a glass at rest and it wants to remain at rest. So I'm going to take this tablecloth and pull it out from underneath the glass. Well, it remains at rest, or very close to it. Okay, let's try that again. See if I can do it a little more smoothly. Bear in mind we have a couple forces acting here. The force of friction, so I can pull the glass like this, and that way we can see we have a frictional force acting on it. Or I can just yank the glass or the tablecloth very quickly, pulling it out from underneath the glass. There you go.
All right, let's look at this from another angle. You can see that the glass stays nearly at rest even when the sheet's pulled away.
In another demonstration of Newton's first law, we're going to take a jar, a note card, and a penny. We have them stacked: jar, note card, penny. And what I'm going to do is pull the note card out while the system is at rest. What you're going to see is the penny at rest remaining at rest. Look at that. The penny remained at rest on top of the note card and fell into the jar. As long as you pull quickly, the object at rest wants to remain at rest and falls into the jar. Okay. So in another experiment that we're going to do here, we have a weight that is suspended by a string on top. There's another string on the bottom. And the question here is, if I pull on the bottom string, which string is going to break first? The bottom one or the top one? And most people think here it's going to be the top string that breaks first, because the top string has a weight of the mass, which is 3 pounds, plus whatever force I'm pulling with down below. However, if I pull very quickly, you can see that I can break the bottom string, this right here, the bottom string, and the top string remains intact.
Let's take a closer look.
But what you can see is that I can break the bottom string and the top string remains intact, because I pull so quickly that the force of my pulling, or rather, the object's rest will remain at rest. The inertia of this mass holds it in place, and it does not break the top string, but allows me to break the bottom string instead. Okay. If, however, I were to pull slowly, if we repeat this and I pull slowly, what's going to happen is we'll break the top string, because pulling slowly, the large mass has, even though it has a lot of inertia, has time to accelerate. It can transfer that force on up to the top. You can see you break the top string. Because of inertia, we can take a large 2 kilogram object and a hammer in one in each hand, and we can hit it. And what you see is it doesn't hurt my hand. I'd never want to take a hammer and just hit my hand. That would be very painful. However, if I put a large object in that it has a lot of inertia, it's not painful because this does not want to accelerate, does not want to move, wants to remain at rest. So hitting it with the hammer doesn't cause any pain. Newton's third law says that for every force there's an equal and opposite force. That can be clearly demonstrated with my fan cart. If here's a fan, and if I turn it on, it's going to blow the air in this direction. Now that very force, the same force that it puts on the air coming in this direction, will be the force the cart experiences in the opposite direction. So the force in this direction of the air will equal the force on the cart in that direction. Watch what happens as we turn it on. You see the cart move this way because the cart's moving this way because the air is being blown this way, the opposite direction. For every force, there's an equal and opposite force.
Okay, we know Newton's third law says for every force there's an equal and opposite force, and his second law says the sum of the forces equals ma. Now, if we combine those two, what we get is negative mass times acceleration equals mass times acceleration. And what we find is the smaller mass has a big acceleration, and the bigger mass has a smaller acceleration. Therefore, in this example, the air, the smaller mass, has a big acceleration, whereas the cart, with a greater mass, has a smaller acceleration.
All right. Here we have the 50-gram pan set up down there over a pulley designed to accelerate our cart forward like this.
Here we can see a picture of what's going on. There's a weight hanging over the edge of the table pulling down with this force of weight, which accelerates the cart horizontally. You can see the mass of the pan is 50 grams.
Here we can see the cart has a mass of 388.7 grams.
So we measure the force of weight of the pan as mass times the acceleration due to gravity of negative 9.8 meters per second squared, and we get 0.05 kilograms. That's the 50 grams converted to kilograms times negative 9.8 meters per second squared. Therefore, the force of weight is negative 0.49 newtons. Now, let's see if you can calculate the rest of the forces that are on the cart based on this information. Remember, the mass of the cart and mu are shown above. Pause it here until you've gotten your answer. Okay, are these the forces you got? I hope so. Let's talk a little bit about why this is. First of all, your force of friction is negative here because it's going left, okay? And forces to left and right can't have the same sign. So if right's positive, left's going to be negative. Also, the force of weight of the pan becomes the force applied on the cart. The pulley changes the direction so you can lose the negative sign, but it is the force applied. Okay, now we're going to use this information to calculate the acceleration and the amount of time it will take to travel the half a meter, 50 centimeters. If you would like to pause it and do the calculations yourself, you can do that now, or just watch as I do them. Okay, here we go. Okay, we use Newton's second law to calculate the acceleration. Bear in mind, you have to add the mass of the pan and the mass of the cart together because both of them will be accelerating. Okay, and you get an acceleration of 0.769 meters per second squared. To calculate the displacement, or the time during this displacement, we use d equals VIT plus 1/2 AT squared. Remember that the initial velocity is 0, so that term can go away, and t becomes the square root of the displacement over 1/2 of your acceleration, and that works out to give us a time period of 1.14 seconds. Okay. So let's watch this thing in action and see how long it takes to go the 50 centimeters. We'll see it again in slow motion. Here, 1/5 the original speed. If you time from the release point to the 50 centimeter mark, you should get about 5.5 seconds.